properties of matrix multiplication?
No, I said we're not. Those properties apply, so like distributive property and associative property apply for matrix multiplication as long as a product exists, but we're not going to demonstrate them. We're not going to spend the time to do that. But what we are doing is we're coming up with another method for solving systems of linear equations where we're using a matrix equation. So we're thinking about taking the coefficients in the system of linear equations and creating a coefficient matrix and then multiplying that by a column matrix that has this number of rows that are the number of variables that you're trying to solve for. Okay, so like in this case, our column matrix X has X and Y in it because we're trying to solve for X and Y. And then is equal to the column matrix that is what each of those linear equations is equal to. And if we think about applying the row by column method for multiplication, right? So taking row 1 times this column, wouldn't it be this sum, right? Equals to 1. And then row 2 times the column would be equal to this. So we could see where this matrix equation matches up with the system. Do we see that? Okay, so let's practice doing that with this system that has 3 equations and 3 variables. Oh, I have typos. Do you see the typos? Those are supposed to be Z's. Z. There we go. Okay, so coefficient matrix first. Times the column matrix with the variables that we are trying to solve for. Equals to the column matrix that has what each linear equation is equal to. Okay, so matrix A, matrix X, matrix B. So really, we're trying to solve for the elements that are in matrix X, right? But we're like, well, wait, how the heck do we do that? So if we think back to just solving a linear equation, like so thinking in real numbers, not in matrices. If I give you the equation AX equals to B, how would you tell me to solve for X? Like isolate X. Divide by A. You tell me to divide by A. What's another way to describe dividing by A? Multiplying by 1 over A. So if we thought about multiplying by 1 over A here on each side, right? That would still give us the X equals to B over A, right? Like that would be isolated. What's another way, using exponent rules, what's another way to write 1 over A? A to the negative first. So if we thought about multiplying, so here, I'll write the 1 over A first. So if we did 1 over A times X equals to 1 over A times B, that's the same as A to the negative first times A times X equals A to the negative first times B. And that's because A to the negative first is A's multiplicative inverse, meaning A to the negative first times A is equal to 1. I'm going to put a little note on here.
So it's reciprocal.
So it's what?
It's reciprocal?
It's the reciprocal, but it's also the multiplicative inverse because that product is equal to 1. So we're kind of circling back to Algebra 1 when you guys talked about like all these different properties of real numbers. And then we're transferring that knowledge to matrices. So 1 over a, or a to the negative first, is the multiplicative inverse of a. Because a to the negative first times a is equal to 1. 1 is the multiplicative identity of any real number. Because any real number multiplied by 1 is itself. Okay, so a to the negative first, or we can call that a inverse, is the multiplicative inverse of a, and 1 is the multiplicative identity of any real number. So any matrix, any m by n matrix, has a multiplicative identity or a multiplicative identity matrix that is a square matrix. So it always has an order of n by n, like same number of rows, same number of columns. And the dimensions or the order is determined on making the product work. So like whether you're thinking about multiplying matrix I by A or matrix A by I, right? The dimensions or the order could be different in order for the product to actually be a product. And I have a typo here. I didn't think it was going to make these little boxes because I didn't want the boxes, but I couldn't figure out how to make it bigger. Okay, so I sub 2 is the 2 by 2 identity matrix. I sub 3 is the 3 by 3. I sub 4 is the 4 by 4 and would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, and so on. What does this kind of look like? What's the identity matrix kind of look like that we've been using? Reduced row echelon form, right? So kind of keep that in mind too. But the identity matrix for an m by n matrix means if you multiply that matrix by its identity matrix, you'll just get the actual matrix. Bless you. So like if we were multiplying matrix A by its identity matrix, but notice that we're doing I times A. So I which is going to be a 2 by 2, that's what that 2 indicates, times A would be 1, 0, 0, 1 times negative 2, 3, 4, 7, 1, negative 1. Which, if we were multiplying A by its identity matrix, doing like A times I would actually have to be a 3 by 3. It would be I sub 3 if we were doing A times I. Do we see that? But then thinking about applying matrix multiplication, so row by column. Okay, so that's 1 times negative 2 plus 0 times negative 2. And then
0 times 3, right?
Yes, I was just making sure you're paying attention.
Okay.
And then 1 times 4 plus 0 times 7. And 1 times 1 plus 0 times negative 1. Okay, and we can move to row 2. So 0 times negative 2 plus 1 times 3. 0 times 4 plus 1 times 7. 0 times 1 plus 1 times negative 1. So we get negative 2, 4, 1, 3, 7, negative 1. If you're like, well, duh. I know. We're just showing that if you multiply a matrix by its identity matrix, it's equal to itself. In the same way that if we multiply a real number by a 1, it's equal to itself. Are we okay with that? Okay.
How do you know when to use I2 or I3 or whatever? Like, how do you know which one to use?
Well, you tell me. So if I gave you I times A, where let's say A was a 3 by 4.
Oh, it would have to be 3 because it has to be 3.
Versus if we had A, it was like a 4 by 7, then I, in this direction, would have to be a
Oh, 7.
7.
Because
I
the
said
order
7.
matters. Yeah, because it's
And then it would be a 4 by 7, right? Exactly. Okay. So using the same thought that we had above, so we had talked about, well, A inverse times A is equal to 1. So if we transfer this to matrices, that's saying, well, the inverse matrix of A times A is equal to I. The identity matrix, right? And both directions should work. So you should also be able to say, or A times A to the negative first is equal to 1. So A times A inverse, I wrote it in the opposite order, right, of what it says in my definition here.
But I thought that there was no commutative property of multiplication for matrix.
There's not. So this is only true if you have a square matrix. So to have an inverse, a matrix has to be a square matrix. So if, and not all square matrices have an inverse. So if a matrix has an inverse, then this product is true and this product is true. That statement's true and that statement's true. So we're going to matrix A and its inverse. So if we look at this, matrix A times A inverse, just using matrix multiplication, let's do it both ways to verify. All right, so doing the matrix multiplication, 1 times 9 plus 4 times -2, 1 times -4 plus 4 times 1, 2 times 9 minus 2 times 9, right? And then 2 times -4 plus 9 times 1. And we go, oh, what's that simplify to? 9 minus 8 is 1. That's 0. 0, 1. What do you know? It's equal to the identity matrix that is order 2 by 2. And if we multiply in the other, so if we switch the order there,
is there ever a case when like a times a to the -1 is equal to I n, and a to the -1 times a isn't equal to I to n?
if it's not actually inverse. So
Oh.
this is like verifying. Right now we're verifying that these two matrices are inverses, and the fact that if they truly are inverses, their product would be equal to the identity matrix.
Okay.
So that kind of gets into like why we're doing this. So then A inverse times A and just for the sake of time, although I think you could probably see this, this ends up also being equal to the identity matrix, I sub 2. So if an inverse exists, an inverse matrix exists for a square matrix A, matrix A is referred to as a non-singular matrix. But if the inverse does not exist, then matrix A is referred to as being singular. That's not something that I'm going to assess you on or anything. Just think of that as like planting the seed for if you end up studying matrices again. Okay, so let's think about this. How can we go about finding A inverse? Because we're up here and we're like, okay, well this should be true, right? But like, how does that work? How do you still determine what A inverse is? Well, knowing that relationship, so knowing the fact that A times A inverse should be equal to the identity matrix. So A times A inverse equals to I sub 2. We have 1, 2, -1, -3 times this matrix is equal to 1, 0, 0, 1. We're like, okay, well, what do we know? We know how to multiply matrices at this point. Like, we have that in our toolbox. So why don't we multiply out the left-hand side? Because at this point, you're like, well, you could try and solve for W, X, Y, and Z using inspection. You could go, well, but you also have to think about like row by column method. That would be really hard. So like, let's actually do the matrix multiplication. And if we do that, right? We would have W minus Y, X minus Z, 2W minus 3Y, 2X minus 3Z. Remember at the very beginning of this lesson last class when I told you, like, we talked about equality of matrices? Like, two matrices are equal to each other if each corresponding element is equal to the other? Well, we have a 2 by 2 equal to a 2 by 2. So shouldn't we from here be able to say, like, W minus Y is equal to 1? X minus Z is equal to 0. 2W minus 3Y is equal to 0. And 2X minus 3Z is equal to 1.
Four equations, four variables. So that's that.
Well, but are all four equations in the same variables? Haven't we actually just created two systems?
Oh,
Two equations,
Oh,
two
yeah.
variables with this? Which, knowing what we know from the previous section, right, when we were solving systems using augmented matrices, either using Gaussian or Gauss-Jordan elimination, this would be this first augmented matrix. And then this would be the other augmented matrix. I'm going to add a page here because I'm going to run out of room. What do we notice about these two augmented matrices?
The same.
The whole thing is the same?
Oh,
The coefficient part is the same.
The left side of each of those is the same. And if you also look, do you notice that the coefficients here, aren't they the same as these coefficients that we started with? So because the left-hand side is the same here, but notice they're equal to different values. Like the first one, 1, 0, the second one, 0, 1. We're actually allowed to combine this into a single augmented matrix because that left-hand side is the same. So we're able to combine that to be 1, 2, negative 1, negative 3, 1, 0, 0, 1. Do you notice anything else that we've been talking about?
The right hand side has become like the identity thing.
Yeah, the right-hand side. So the left-hand side is the coefficient matrix that we started with, right? Left-hand side is the coefficient matrix. And the right-hand side is the identity matrix. What is it, like, what was our goal in, like, getting to here? What were we trying to do, you guys? Find the inverse of A. Find A inverse. And we've, like, gotten to the point where now we have this augmented matrix. which really represents solving two systems simultaneously. We know how to solve a system in an augmented matrix using, what does your calculator do though? Gauss-Jordan elimination. Gauss-Jordan, but not on our calculator. We're going to do this by hand. So using Gauss-Jordan elimination, we can actually find what our inverse matrix is. So here's what we're going to do. We're going to use Gauss-Jordan elimination. And the right-hand side, so that identity matrix, is going to end up turning into the inverse matrix. So we're going to, here, let me write this down just for so you can reference it. So we're going to use Gauss, that's not how you spell Gauss. We're going to use Gauss-Jordan elimination to transform the left side to the identity matrix, right? Because that's essentially what Gauss-Jordan elimination does, right?
So REF and the identity matrix are basically the same thing.
Well, the identity matrix is in our REF, right? Reduced row echelon form. Okay, if it's in an augmented matrix. And the left, and the right side to A inverse. So using what we already know. So we already have one in that position that we want for reduced row echelon form, but why don't we use our row operation? So I'm going to think about multiplying row 1 by -2, adding to row 2 to replace row 2. So is that 2? And that ends up being -1. And then -2, so plus 0 is -2, 0 will be 1. Okay, so we're almost there. Let's multiply row 2 by -1 and replace row 2. We're in row echelon form after we do that, but we want to go all the way to reduced row echelon form. Okay, and then let's use this leading one to make the one above it 0. So we can actually just think about adding row 1 and row 2. To replace row 1. Okay, so now this is I2, I sub 2. This is A inverse. So A inverse is 3, 2, -1, -1, which you could have found if you had actually solved this system. Using substitution or elimination. And you could have then had x, y, z. No, w, x, y, z. But this is another method for finding A inverse. Questions? So we're going to continue talking about finding the inverse of a square matrix. So it has to be a square matrix, and not all square matrices have an inverse.
Oh wait, did you record this part or no?
Yeah, we're recording.
Oh, okay.
So we're going to go through using the method that we just used to find an inverse matrix if it exists. So we're going to make the augmented matrix where it's the coefficients of the matrix A on the left, the identity matrix on the right-hand side that has the same order as matrix A, and then we use Gauss-Jordan elimination to get the identity matrix on the left-hand side and the inverse on the right-hand side. Now sometimes there is no inverse. So it would end up being like you'd have a false statement, like you couldn't solve the system. And then you could verify, you could do it with your calculator. We're not really going to do this step. We're going to trust that we did it correctly. So let's go through using this method and find the inverse matrix for matrix A. So setting this up, on the left-hand side we have 2, 5, 3, 8. 1, 0, 0, 1. Okay, and then thinking about using Gauss-Jordan elimination, we need a 1 in row 1, column 1. So to do that, I'm going to think about multiplying row 1 by 1/2 to replace row 1. And I realize we have to deal with fractions. It is what it is. Okay, and now we can use that leading 1 to make that 5 into a 0. So we'll multiply row 1 by -5 to add to row 2 and replace row 2. Do we see why we're doing that? Okay, so that ends up being 0, 1/2, -5/2, and 1 in row 2. And then we can think about multiplying row 2 by 2 to make 1/2 into 1. But how would you do that?
Multiply row 2
Oops.
by 3 and add them to row 1 before you change row 2 into the 0, 1, -5.
Sure, you could do that. I had thought about then multiplying. I always go in the same order, but multiplying row 2 by -3/2 and adding to row 1 to replace row 1, we'll get the same thing. So 1, 0, 8, -3.
Wait, what's 15 over? Oh, that's 17.
0, 1, -5, 2. Okay, so A inverse is 8, -3, -5, 2. Sorry, that sounded painful. Now, for 2x2s, there's a special formula that you could memorize
Oh, I like that a lot better.
in order to come up with A inverse. This, if any of you are taking the SAT, I believe this like comes up. Which your calculator, I believe your calculator can do it. Find it. Calculate the determinant. Give me a second here. Yeah, so if we go second matrix, yeah, the first option on the matrix menu is determinant. So if you wanted to use your calculator, you could. And maybe we'll do this by, let's just check with this one, and then let's also, so the determinant is just AD minus BC. So this is for a 2x2. Now there are determinants that can be calculated, and there is a formula for like a 3x3, and there is for like a 4x4, but like knowing those is just kind of crazy to memorize. Give me a second here. Okay, your calculator I don't think your calculator can find the inverse, but you can have your calculator. Let me see. So let's do this by hand for confirming this formula. So A inverse would be equal to 1 over AD, it would be 2 times 8, minus BC, which would be 3 times 5. And then times, you switch the A and the D, and then you take the opposites of the B and the C. Okay, so in this case, 16 minus 15 is just 1, so you can see like we just ended up with A inverse. Right, using this.
The determinant's 0, right?
No, it's 16 minus 15. I'm looking at the one we just did the long way.
Okay.
Okay. I mean, like, using this is like having to memorize a formula. This other way is more like a methodical way of finding the inverse versus like having to memorize a formula. Now, like, if we were trying to use the formula for this guy, which I think is what Tony was looking at, you'd be like, oh, A inverse equals 2. It's a 2x2. So then you do AD minus BC, right? So AD minus BC and then times, you switch and then take the opposite. But then you're like, well, wait. That ends up being 1 over 0. Because the determinant is equal to 0. So then you're like, well, wait, that doesn't work. So we would actually say in this case that this for matrix A, that A is not invertible. And therefore A is singular. I would just expect you to be able to like say that A inverse doesn't exist. Okay. Why don't you, either on your own or in like who you're sitting with, go ahead and use the method. This is a 3x3, so you have to use the like setting up the augmented matrix and using Gauss-Jordan elimination. But why don't you go ahead and find A inverse? This one's not too bad. It's a 3x3, but it's not too bad.
So like how our calculators on the quiz, can we like row echelon form stuff, the calculators, and then work from there?
Maybe. Let me think about it. Practice the Gauss-Jordan elimination for this one. How would it wouldn't really help you.
You have to answer faster because you should do less.
How, but it's not setting up.
Because once you get to row echelon form, you just have to do it.
Oh, because it ends up being with the two, because they have to be square matrices, so it would.
So you get pretty close.
Do it by hand for this one. You should know how to do it by hand.
Oh, I want to.
I'll let us use the calculator for when we're actually solving the matrix equation. You can get credit for that.
We'll do some solving.
I was initially doing it all by hand, but I'll let us do it by a calculator because it is painful. But you should know how to do it by hand. Are we still working on it, you guys?
Yeah.
Okay. I know, these are long.
I'm sorry. I'm just.
No, don't say sorry. That's fine.
Oh, that's okay. Did you finish?
Yeah.
You got this, right? Oh, okay. 0, 1, 1. Oh,
Is that the right answer?
0, 1, 1.
Okay, why did I?
1, -1, -1 equals 2, 1.
That's what I got.
Yeah, the first row, I don't know what I did wrong.
Wait, what's the last one?
0, 2, 1.
You're too
Oh,
bad.
okay.
Oh, it's just the map row.
Mathed it. Mathed it.
I forgot on the last step, there's actually, was -1 row to actually do something.
Okay. Is it okay to move on? We safe? Okay. So kind of putting it all together, right? We had talked about if we set up our matrix equation, right? We have A times X equals to B. Those all being matrices, right? I'm going to put their order on there too, actually. Let's say A, which is an n by n. So in this case, this kind of also limits the systems that you're solving, because you have to have n by n. Like if you had more equations, it wouldn't work. So A is an n by n, and then X would be an n by 1, and B would also be n by 1. Okay? And we had talked about a linear equation in the form AX equals to B. We're like, oh, divide by A, but wait, there's another way to think about that, by multiplying by the multiplicative inverse. So here, if we thought about multiplying by A's multiplicative inverse, which is n by n, and order does matter here, right? Because if we were multiplying by A, like B times A, that product wouldn't exist. Okay, so if we do that, this turns into I sub n, meaning that X is equal to the product of A inverse times B. So that's our method for solving the system, is that we need A inverse. So let's do that here. Let's first think about setting up, well, let's identify what A would be, X and B, right? So like if we were thinking about matrix A is the coefficient matrix. Okay, X is like the variable column matrix. And B is also column matrix.
Wait, I just realized it's 3 by 3. We can't use the determinant thing.
No.
Oh.
So we could by hand, but this is where I was saying, I'll go with what Sophia was suggesting. We can use our calculator. But you know how, or by hand, with Gauss-Jordan elimination. Okay, so going to your calculator, go ahead, second matrix, and then when you're editing the calculator, the matrix in the calculator, you're going to make the dimensions of the of the matrix a 3 by 6, right? Because you're having to think about, here, I'll write this all down. So on the calculator, for finding A inverse, right, you're setting up 1, 0, 2, 1, 1, 3, negative 1, 1, 1, 1, 0, 0, 0, 1, 0. Okay, so in the calculator, when you're editing matrix A, so you go second, inverse, and then you're going to edit. You're going to make matrix A a 3 by 6 to type this in. Okay, so 1, 1, negative 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 2, 3.
Wait, it
One,
literally just gives you the
zero.
inverse matrix, right? If you do it reduced row echelon form.
0 on the right hand side, yeah.
Wait, you can't see it.
Oh wait, what happened to mine?
Bruh.
Ugh. Okay, wait. 0, 1, 1, 0, 1, 0. Why did that not save? 0, 1, 0, 2, 3, 1, 0, 0. My keys are sticky. Okay, and then we're going to quit. So second mode.
I don't know,
Yeah.
dude, I think you might just have to stick with doing it.
Oh my gosh.
And then you're hitting second
No. So
inverse again, but you're going over to math and then RREF. And then you're calling up matrix A. Which would be a 1. And hit enter.
Can you just tell me the answer because it just cuts off? Oh my gosh.
Yeah. Okay, so then what you should see on your screen, what happens is you have 1, 0, 0, 0, 1, 0, 0, 0, 1. There's no line there, but we can write it. So -1, 1, -1, -2, 3 halves, or you can use 1.5, -1/2, 1, -1/2, 1/2. Let me fix this.
Oh wait, I actually guessed that.
Okay, so this is A inverse. So then when we go back to trying to solve this system, we go, okay, well, X is going to be A inverse times B. So taking A inverse, and multiplying by B will give us our solution. And you guys, if this is a 3 by 3 and this is a 3 by 1, this product is going to be a 3 by 1. Okay. So we'll have -1 times 3, and if you multiply on your calculator, you could also get the answer, but for funsies, and because you need to know matrix multiplication for right now, okay, we end up with 0 to -1.
That's so anticlimactic.
Really?
For that many like halves to be in the inverse.
Wait, isn't it 5? I think it should be 5.
No.
Oh wait. Oh, it's -1. Are you kidding me?
So what that means is that our solution to the system, because you're like, whoa, we were solving a system doing all that. Gauss-Jordan elimination ain't seeming so bad. Especially because you're technically supposed to use it by hand. But the solution is 0 to -1.
Also, Gauss-Jordan elimination can be used for like other matrices that aren't square, so it's more flexible. Kind of.
Mm-hmm. Mm-hmm. What?
That was a lot of work just to get the same answer that we've been getting like
With other methods, I know. But remember, it's the process and understanding the process that is transferable. Because it uses things that are in you already have in your toolbox. But you're right, another method. Do I want to make you guys do this? Maybe we'll save this as like a warm-up for next class. Okay, I'm not going to, you're going to have an assignment, but it won't be that long. And I'll put directions. So for finding A inverse, you can use your calculator. Yeah.